So, today is January 3rd, 2012. Happy New Year. Happy 2012 of your senior year for most of you. Let's finish up our discussion of estimations, and we're going to be looking at estimations of population means today. All right. Now, I know it's been 2 weeks since we've talked, so let's revise some of these earlier memories. We started with this idea that we use things like a sample mean or a sample proportion as an estimator to a population mean or a population proportion. In the sample proportion case, we had this beautiful recognition that things that come from categorical variables, they follow from initially the binomial distribution, but if we convert those to proportions, the distribution of sample proportions is nicely normal. And that our estimate of the standard deviation of that particular normal distribution was easily calculated, or at least easily estimated, with this thing called the standard error. We're going to do the same thing today with population mean. Again, the vision that I want you to think of is that one sample mean is just one number in a big distribution of sample means. These sample means, this distribution of X bars, have characteristics that we can exploit. And those characteristics have to do with what we know about the mean of the distribution of sample means, the standard deviation of the distribution of sample means, and this new thing that we're going to call the standard error. And then lastly, the shape of the distribution of sample means. We want to look at all of those things so that we can do these great probability calculations, because those probability calculations are the evidence that we use to know whether something is statistically significant or not. But let's get back. We're going to only look at confidence intervals today. All right. So what are we going to do? Well, we're going to construct and interpret a confidence interval having to do with the population mean. We're going to be able to do calculations to determine whether we have a large enough sample size to meet our margin of error. We want to describe what the margin of error does and does not tell us. Remember that the margin of error only has to do with the stuff related to sampling variability and not having to do with bad sampling technique. And then lastly, we want to determine sample statistics from the confidence interval. So let's jump in. We did this exercise back in 8.1, and we had this idea that I give you a bunch of sample means, and then we say, well, what do we think? What do we think the real mean is? Give you a bunch of sample means, and then you could say, well, based on your sample mean, what do you think the real mean is? Based on your sample mean, what do you think the real mean is? Meaning the population mean. Remember, we have to do this all the time. We sample all the time, wanting really to know what's going on at the population level. We've got this worry about global warming. We'd like to know what the true mean temperature of this Earth is. Do we have the ability to be at all places at all times to do all that data collection? No. Can we sample them? Yes. And based on that sampling, do we think we're going to get exactly the right answer? No, but we think we're going to be close. Now, how close is close enough? Well, in determining whether this Earth is warming or not, we need precision of about 1/10 of a degree. A shift of 1/10 of 1 degree has huge consequences for us. A shift of 1 whole degree could be cataclysmic. So, we need to know these things. We need to know these things even though we can't know everything. So, we had said, way back when we did this exercise in 8.1, that, you know, if I had some estimate, let's, in this case, call that estimate X bar, that estimate is the center of an interval where we think the true population mean lies. And then we had this thing called a critical value. On that day, we called it Z star. We had different Z star values based on different levels of confidence. You want to be really, really confident, then your Z star value gets to be really, really big and encompass a lot of different possible values for the population mean to fall into. You don't need to be that, you don't need, or you can afford to be less confident, then your Z star value will get smaller and will encompass a smaller range of numbers. And then we had this thing, the standard deviation of the statistic, and we had talked about the fact that sigma divided by the square root of n was the standard deviation of the distribution of sample means. And all of that is perfectly true, and all of that's really, really great, except there's one problem with this formula. This is a sample mean. Why don't we just use the population mean? I just talked about this about 2 minutes ago. Why don't we just use the population mean? We don't know what it is. It's too hard to get. So we're going to use X bar, right? We use statistics instead of parameters because parameters are really hard to get. Okay. So we're all okay with the fact that we have to use X bar there. Well, let me put a green circle around that thing. The symbol sigma. What does sigma represent, please? Standard deviation. Good. I need more, though. Not just the standard deviation. The standard deviation of, and your choices are sample or population. Is sigma a statistic or is sigma a parameter? Jason, you say statistic. That's what you said. Anyone got any disagreements on that?
Parameter.
Okay. And now, are you just being contrarian, or do you really know that it's a parameter?
I don't know.
You don't know. Okay. In general, we use Latin letters, our normal ABCs, for statistics. In general, we use Greek letters for parameters. The last time I checked, sigma was a Greek letter. Sigma is a parameter.
Thank you.
Sigma comes from, good guess, sigma comes from population level data. Wait, why are we using X bar? Because we can't get U easily. It's too hard. It's too expensive. Then how is it that we know sigma? This seems... It's like, how is it that I know something from the population level like standard deviation, but I don't know something from the population level like mean? And the answer is, we hardly ever know what sigma is. While this is a perfectly true statement, if you know sigma, we hardly ever know what sigma is. This is not a very useful formula for the majority of things that we do, because we hardly ever know sigma. So that's the problem with this formula. Let's get rid of it. Let's move on. Okay? So we did all these calculations using X bar, using sigma, using n, and I said, if you knew sigma, it'd be great. But we don't often know sigma. We hardly ever know sigma. So we need a new plan. We need a new plan. okay, we recognize in the rare instance that we know sigma, that the confidence interval calculation is going to be x bar plus or minus d star times sigma over root n. It should be in your notes. It's 8-1. And again, I'm going to claim right now, while that is a true statement, not a very useful statement, because we don't often know sigma. And if we do, someone's just making it up. All right. So can we move on? All right. So again, we're going to live in bogus land for a little bit longer. We're going to live in this world where we supposedly know this thing that's typically unknowable. For example, what if I wanted to calculate how big does my sample need to be for a particular margin of error when I know sigma? And again, we don't usually know sigma. Well, we know that the margin of error is coming from this z star times sigma over root n part of that formula. And if we solve for n, so that we can find out how big our sample size has to be, we will also need to know what z star value that we're going to need. Did I show you the shortcut on how to find z star? So if I asked you, what's the z star value for a 95% confidence interval, you'd be able to look that up?
Yes,
Could you get that table out? So I'm going to make more references to that table. Okay, so what is that z star value for 95%? 1.96. And other famous z stars are things like for the 99% confidence interval, 2.5. Okay, and then 90, like 1.645. Okay, so you know how to find a z star value. So, but before you find z star, you have to know the confidence level. You need to know the value c. All right. And again, what you end up having, if you're in this situation where they say you need this margin of error, and you get to determine your sample size, you're going to end up plugging in what you know from this equation. Oh, if you know the confidence level, you know the z star value. If you know sigma, and again, you rarely do, you plug it in there, and if you're given the margin of error, that leaves you only one unknown, and that's the letter n. I think what we'll do is, I think we do an example of this. I hope so. Anyone need more time on this slide? No? Okay. So researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey. We like that estimate to be within 1 milligram per deciliter of the true value at the 95% confidence level. A previous study involving this variety of monkey suggests that the standard deviation is 5 milligrams per deciliter. So it sounds to me like we know sigma. It sounds to me like our margin of error they would like to be as 1. They would like the 95% confidence interval, so we have enough information to find out what z star is. 1.96. And now we can put all those pieces together. Z star times sigma divided by root n needs to be less than or equal to our margin of error of 1. And now we're going to because no one complains if the margin of error gets too small. So and because it's unlikely that since the sample sizes only come in whole values, it's unlikely that we're going to get exactly 1. So when we when we don't get the exact answer, we always want to get so that the margin of error is smaller than that. All right. Now we have algebra. What I typically do is I bring the square root of n up there, and I take this 1 and I divide it. I divide, it's like I multiply both sides by root n. It's like I divided both sides by the 1 that was on the other side. And because I don't like that square root there, I'm going to need to algebraically get rid of that square root. And I'm going to square both sides. So my answer is going to be 1.96 times 5 divided by 1 squared. And that's our number that's going to be less than or equal to n. So if I had some calculator help here, what was that? 96.0403. It hardly really matters, but we need to be careful of this one last step. Can I really have 0.04 of one of these monkeys?
No, you gotta round up.
Got to always, in these cases, round up. Exactly, Jason. So we need a minimum sample size of 97 monkeys. And that's a typical question that we would ask you. How big is your sample size? This is a very real question. Real researchers have to answer the question, how many monkeys, how many, whatever do we have to do in order to get to our margin of error? Okay. Let's go on. Now, as I have been alluding to since the beginning of this lecture, well, what if we don't know sigma? What if we don't know sigma? What's reasonable? Well, here's what's reasonable. When I do a sample, I get a sample mean. And we use that as an estimator of the real mean. When I do a sample, I also get something called the sample standard deviation. And when I divide x bar minus mu over sigma over root n, I get this thing called the z statistic. We've been working with z's all year, so none of that's really new. But what if you didn't have access to sigma? What could you use in place of sigma? If I didn't have the parameter version of standard deviation, what could I use?
The statistical version.
Jason, you are on a roll. The statistic version of standard deviation. But you know what? That Z formula doesn't have a S. Remember, we use S, the Latin letter, for standard deviation when it's coming from a sample. It has sigma. So when we do what's reasonable, you don't have sigma, use the next best thing. Let's use S. When we don't have sigma and we use S, we don't get a Z distribution anymore. If we took samples from a known population with mean mu and standard deviation sigma, if we calculated all those Z values from that population, we get a Z distribution. But when we don't know what sigma is, we don't get a z value anymore. When we use S instead of sigma, we get a brand new statistic. Alright? Now, a couple things about the statistic. When you sample from a population and you get an X bar, is your X bar exactly the same as the mean that you're trying to estimate? Who's going to make my birthday really happy by give me some great insight?
Can you repeat the question?
When you sample and you get an X bar, is that X bar exactly the same as the mu that you're trying to estimate?
Can't.
Okay, can't be. You have me up to can't be. Okay,
It probably could be.
it might happen, but it's rare. Okay. And the idea that we have that the X bars are typically never the same as mu is this thing called sampling variation. Okay. Second question. When I do a sample and I get an S, a statistic version of the standard deviation, a sample standard deviation, do you think it's going to be exactly the same as sigma? Why not? For the same reason, because there's sampling variation. Every time we do a sample, while S may be similar to sigma, it's not often, hardly ever, the same as sigma. In the same way that X bar is hardly ever the same as mu. They're similar, they're not the same. So when we create this new statistic, there are two things going on here. X bars are varying all over the place, and S's are varying all over the place. It's varying in two different ways. Well, because it's varying in two different ways, the one thing that we do know is that the way that the distribution of that new statistic, X bar minus mu divided by S divided by root n, whatever it is, it's not normal. Don't call it a z. Well, if you're not going to call it a z, what are you going to call it? Well, maybe because it's my birthday, we're going to call it the t distribution. Well, this is interesting. It's called the t distribution, but originally when it was developed, it wasn't called the t distribution, it was called the student distribution. Now, the reason it was called the student distribution is very interesting as well. The man who did this work about trying to find out how these things happen when you don't know sigma, which we hardly ever know. The guy who did this couldn't use his real name when he did the statistics because his profession was an embarrassment to the statistical community. Like many statisticians, this guy worked in industry, manufacturing a good. And, of course, we want to minimize the amount of variation in a product produced. We would like absolute consistency in the products that we produce. This is why McDonald's is so successful. Not because it's good, but because it's consistent. So the man who developed this statistical technique produced a product that was an embarrassment to the statistical community, so he published his work under a pseudonym.
I wonder why people like this argument and think that McDonald's is the best fast food restaurant. Burger King out there.
I like one. Yeah,
Yep. I was hoping to bring them in with this idea. This guy produced a product that was so embarrassing.
Like Tampa?
Like Hammer. No, the guy produced a product in a town called Dublin.
McDonald's don't even need commercials.
Okay. So we'll never finish that story.
in the male, was it the adult sex industry?
That's Amsterdam, not Dublin. The product produced in Dublin is Guinness beer.
Oh, so embarrassing.
For some people it is. Okay, so the student distribution, the T distribution, which is not normal. If it's not normal, what is it? Well, like the Z distribution, the T distribution is symmetric, has a single peak, and it peaks at 0. However, because two things are varying on every single sample, both the X bar and the S are varying, there's more variation in this distribution. We say that this distribution has more area in the tails. So that if you compare a T distribution over many, many samples to the same distribution if you did the Z calculation with the known sigma, the T distribution has much more stuff out in the tails because of the two things that are varying simultaneously. Now, this is not always true with the T distribution. But for small sample sizes, the T distribution has a lot more in the tails. As the sample sizes get greater, S becomes a better estimate of sigma, and the amount that's in the tails gets smaller and smaller. So we have this new thing that instead of Z, which is consistent no matter whatever the sample size is, the T distribution has more area in the tails in smaller sample sizes, and the T distribution gets smaller and thinner as the sample sizes get bigger. Now, we need to then know what are we going to call this sample size relationship. Okay? We'll get to that in a second. The big thing, though, the commonality between the Z distribution and the T distribution, though, is still this idea. It will tell us how often something happens, how often is some outcome extreme. And like the Z distribution, I think someone wrote on their test, they calculated a Z value of like 70. And automatically you went and said, 70? That's extremely unusual. Same thing's going to happen with the T values. T values, when they're really far from 0, they're really unusual. When they're really close to 0, they're not unusual. All right. This idea, though, that the T distribution will have more in the tails for lower sample sizes and less in the tails and becomes more Z-like over time, or over as sample sizes increase, this idea of sample sizes affecting things, we're going to summarize with the two letters DF, degrees of freedom. We're going to say that the T distribution varies with the degrees of freedom, and those degrees of freedom is related to, but not exactly the same as the sample size. Can you get out your probability tables, and can you find the table that that has the T chart in it? I think it's called table B. You see it? Look down the far left-hand column. Do you see the heading for that column?
Yeah.
DF, degrees of freedom.
Yeah. Yep.
All right? And what we're going to have is that we are going to have different degrees of freedom that lead to different T distributions, and each one of those degrees of freedom leads to a different set of probability numbers. I want you to understand that there's a lot less information on this T chart than there is on the Z table. Okay. Essentially, each row in the T table is a summary of an entire Z-like chart. because things vary with degrees of freedom, they had to do a lot of summarization. One summarization row is at the very bottom, where it says infinity. The line that says infinity, the one that I also told you we called it Z star. That one line summarizes things that are going on in the whole Z table. Each one of those rows represents a summary of an entire distribution. There's a lot of condensing on this table. All right. So, how do we find degrees of freedom? Easy calculation. Degrees of freedom in this case is n minus 1. Sample size minus 1. So, if my sample size is 15, I have 14 degrees of freedom. And that means when I use my T-chart, I will only be looking at the row that says DF is 14. What if I have a sample size of 50? I would have 49 degrees of freedom. And then you would go to your table and you would look for the line that says 49 degrees of freedom and you would come up
What if there's no line?
empty. If there's no line, what do we do? Excellent question. You're going to be faced with this in many situations. Are you ready? Another description of the T-table with more area in the tails is that it is a more conservative Z-table. Now, in my personal politics, I am not a conservative. But as a statistician, I am conservative, meaning I'm not willing to make mistakes. To be conservative is to not willing to take chances. Now, if you had 49 degrees of freedom, and you know as the degrees of freedom got bigger, they removed things from the tails. Bigger degrees of freedom would be less conservative. 49 degrees of freedom, if you had to go bigger or smaller, and again, what I want you to think is I'm going to be more conservative. I'm going to pretend I have less data than I have. So if you have 49, you are going to use your table and you're going to look up the line that says 40. You're going to be more conservative. You are going to pretend you have less data than you have. All right, so the T-distribution has degrees of freedom n minus 1. And data that come from approximately normal distributions will also follow the shape of that T-distribution. Okay, there's another red flag. I don't know sigma, so I use S, and that has some problems. Okay, here's this next problem. I can use this as long as the population is approximately normal. Well, actually, it says here the statistic will have the T n minus 1 distribution as long as the sampling distribution is close to normal. How do we, what's the rules for this? Okay, so I get my sample in, right? And from that sample, I get an X bar. Okay, that's good. I get an S. That's good. I can do the T calculation. And then I have to ask one more thing of my sample. I got to ask, do you think you came from a normal distribution? And of course, we don't know what's going on at the population level. So we look at the sampling distribution and we say, is there any evidence of non-normalness? Meaning, is there skewness? Are there outliers? Because if you have skewness or outliers, perhaps you didn't come from a normal distribution. So we look at the sample distribution and we ask, are you normal? Are you normal enough? And in the absence of skewness and in the absence of outliers, we'll say, yeah, you're normal enough. Okay. When comparing the density curves of standard normal distribution and t-distribution, several effects are apparent. Okay. I don't know if you can you make out that image very well?
Yeah. Looks like a bell-shaped curve.
It looks like a bell-shaped curve. The t-distribution is a bell-shaped curve. Okay, let me hit the high points here. If I do sampling and I only have if I do sampling and there's only 3 things in my sample, my degrees of freedom are 2, and I get a t-distribution. Let's call this line t sub 2. A t-distribution with 2 degrees of freedom, meaning my sample size was 3. What happens when my sample size goes up? Less things in the tail. If there's less things in the tail, where did they go? Into the hump. So with a larger sample size, let's say a sample size of 10, which means we have 9 degrees of freedom, I would get a different t-distribution. By the way, it's always centered around 0. What if I went really, really big? What if I had an infinite sample size? You get even less in the tails, even more in the hump. And with an infinite sample size, we have a special name for that t-distribution. It's a z-distribution. As sample sizes increase, the t-distribution looks more and more like a z-distribution, like a normal distribution. All right, let's continue on. Let's get rid of my drawing. The density curves of t-distribution are similar in shape to the standard normal curve. The spread of the distribution is a bit greater, more in the tails. T-distribution therefore have more probability in the tails and less in the center. This will come up even more when we look at the next thing in chapter 9. Okay, and lastly, as the degrees of freedom increase, the t-distribution becomes more and more normal. It looks more like the standard normal curve. All right, I think we got to get to the point where we start reading some stuff off of Table B. Are you ready for Table B reading? All right. So, we want to construct a 95% confidence interval based on some mean that's from a normal population and sample size is 12. What line on that table are we going to use? 11. Sample size of 12 means 11 degrees of freedom. And now we're going to put the two pieces together. Let me bring up my t-table. There we go. There's my t-table. Nope, that's not t-table. That's a z-table. There's my t-table. All right. So, remembering again that we had this formula to start with. X bar plus or minus z star times sigma over root n. That's what we started this whole lesson with. Our new version of the confidence interval calculation is X bar plus or minus T star multiplied by S divided by root n. Couple more names. This part is called the standard error because it's no longer the standard deviation of the sampling distribution. And like we had said before, this stuff is called the margin of error. In order to complete this calculation, we need an X bar. Oh, we get an X bar when we do the sampling. Check. Got that handled. We need an S. Oh, when we do a sample, we can find the standard deviation of that sample. Check. Got that. We need an N. When we do a sample, we know how many people or things that we sampled. Got that. So the only thing we don't know now is T star. What? S is the standard deviation of the sample. So if you do sampling, you had all those raw numbers, you would be able to calculate the standard deviation within that sample. All right. Now let's finish it off. We got to find the T star value. T star value is found by taking the proper degrees of freedom. In this case, we said 11, and then we have to cross it with the confidence level that we're interested in. And where those two things cross is the T star value that you would use for the confidence interval calculation. So 11 degrees of freedom, and way down at the bottom of our list, our confidence level of 95%, and the cross of those two places leads us to a T star value of 2.201. Now I'm running out of time, but I just wanted you to think and do a quick comparison in your mind. We started this lesson knowing that the 95% confidence interval for Z star was 1.96. This number is bigger than that. Why? So, because since we have less information, we don't have this sigma, which we hardly ever know anyway. Since we don't have sigma, we have to have wider confidence intervals to be sure that we capture the true mean. All right. There was an assignment that was, I think I gave you the exercise numbers when we started this chapter. You can do some of those exercises. We are on slide. Yeah, I did. Please sit down. Please do not ruin my birthday with your overzealous standing up. Okay, we are on slide 11 out of 20, which means we really have about another 6 slides to go. I want you to do something that you haven't done for me before, or some of you, at least some of you haven't, and that is, I want you to attack the homework tonight.